Hi, welcome back to the channel. So we're making pretty good progress. In the last two videos, we talked about how bits are sent on a wire using layer 1, and we discussed MAC addressing in layer 2. But before we get started, let's review our use case for this series. It's a simple network call that I'm using to tie all these layers together. Okay, let's say you're on your computer at home and you want to bring up a web page. A request is made, and an HTML response is returned. Today I'm going to focus on the part of the URL called the IP address. And to keep things really simple, I'll only be talking about IP version 4 or IPv4. In my last video I talked about how network cards already have an address called a MAC address. And I made an analogy that a MAC address is kind of like a VIN number of a car. It's created by the manufacturer and it's permanent, or at least semi-permanent. So this begs the question, why do we need another address? Why don't we just use the MAC address instead of an IP? And there's a few reasons for this. Number one is portability. So sticking with the car analogy, we need an identifier that can change based on the location of the vehicle or its intended purpose. Another reason we need IP addressing has to do with sizing in something called a broadcast domain. So let me explain that next. Let's make our web request again, using a URL with an IP address. But we do have a problem. The formatting of the bits traveling down the wire layer 2 only have a MAC address as the destination. We're not even at the point where we can view an IP address. If you see my last video, you already know how we're going to solve this problem. First, we'll make a request to all the machines on the local network, and this request contains the IP address that we're looking for. A broadcast request is then sent to all the machines at layer 2, and one of these broadcast requests finally reaches our web server containing the correct IP address. A response is sent back with the MAC address of the web server, and now our workstation knows the MAC address of the web server. And it'll use that address to start making requests. So that's a roundabout way of reaching an IP address. However, what happens if we have a larger network with potentially hundreds or thousands of servers? Every time we want the MAC address of an IP, we'll be making broadcasts to all the machines. And this can create something called a broadcast storm, which can cause all kinds of problems. So we need a way to break up our networks to reduce the broadcast load. You can see I now have 3 separate networks with 3 separate broadcast domains. But it would be nice if we could still connect to the other networks and allow them to communicate between each other. To accomplish this, I'll introduce a new device called a router. You can think of a router as a computer with multiple network cards that can direct traffic based on the IP network. You can also see I've highlighted some of the numbers in red. This helps to differentiate the 3 networks. But for now, let's just focus on one network and break down how the IP address is structured. An IP address has 4 sections. Each section is made up of a byte, or 8 bits, and is separated by a period. And another name for each byte is an octet, and that's the terminology I'll be using for the rest of this video. Now let's talk about sizing. The 4th octet, when it's full, has a value of 256, or 256 addresses. If we combine the last 2 octets, we now get 65,000 addresses. With the last 3 octets, now we're up to 16 million addresses. And the total number of IP addresses in IP version 4 is roughly 4 billion addresses. Now, 4 billion is a lot, so we need a way to break this up into more manageable networks. After all, one of our goals is to reduce the chance of a broadcast storm, and 4 billion addresses is a pretty big storm. So to define the size of the network, we need another piece of information in addition to the network address that you see here. And that's called a subnet mask. Now just like our IP address, the subnet mask has 4 octets separated by periods. The subnet mask has 2 parts. First, the 1s are used to identify the network. The remaining 0s will define the number of hosts we have available. This will be the number of machines that we can connect to the network. In this case, we have 256 host addresses that will be available to use on this network. Let's take a closer look at this network. You can see that the 3rd octet is a 1. We could have another network with a 2 instead of a 1. And that means we could have 2 different networks and they would each have 256 host addresses, or 512 for both of them. Now you may have noticed in my earlier slide that I mentioned that 254 addresses are actually usable out of the 256 addresses. That means we're missing 2 addresses, so let's see where they went. The first address is reserved as a network identifier. This address can't be assigned to a host. Its purpose is to define the network and it also lets you know where the host addressing will begin. The last address can't be assigned to a host either. It's used as a broadcast, which is similar to a broadcast in Layer 2. This is a special address that allows us to send a request to all the machines on a particular network. So that leaves us with 254 available addresses that we can assign to host machines. By convention, the first available address is usually used for the router connected to the network, and this router goes by a number of names, sometimes called the default route, or the gateway address, or the route of last resort. Again, this is just a convention. In practice, you can use any available host address for your routers. Okay, let's take another look at the subnet mask for each octet. There's a pretty huge jump in the number of available hosts, and this doesn't really give us a lot of options in terms of sizing our networks. For example, what if we want our network to have only 100 addresses? Is that even possible? The good news is we actually have a lot of flexibility. You can mask off a network within an octet. The only rule is that the ones in the subnet define the network, and the zeros define the host range. So in this example, we're splitting our octet in half to give us 128 host addresses. With this example, the 0 address is used for our network identifier, just like before, but this time our network ends in 128 instead of 255, giving us a host range of 1 to 127. Now before we get too far, I want to point out that there's another way to define a subnet mask that's different than the 4-octet notation that you see here below. Since the subnet mask in this example has 24 bits, we can use /24 as our naming convention, giving us a subnet mask that looks something like this at the top. Now, both naming conventions are very common, so it's good to be aware of both of them. The top naming convention is called Classless Interdomain Routing, or CIDR. You can look up CIDR addressing on Wikipedia. They have a page with a table towards the bottom showing all the available CIDR ranges. Let me see if I can find it really quickly. Here we go. And this comes in handy when you're trying to size networks for your organization. Now let's dive into where IP addressing actually fits into the OSI model. We'll start with our simple /24 network, but you might be wondering, where is the IP address defined in here? To the right, you can see there's a payload section in the Ethernet frame, and that payload can be up to 1500 bytes in size. If I open that payload up and inspect it, we'll see another structure with another destination address at the bottom, and this is where the IP address actually would go. Okay, so we're finally getting to a good point where I can start to connect the dots of the OSI model, but let me use an analogy to better explain this. Ultimately, we want to get a file from the web server called index.html. So let's imagine we're writing a letter to our web server and asking it to return a file called index.html. Next, we'll place that letter inside of an envelope. For the address of the envelope, we'll use port 8080, and we'll call this envelope layer 4. Now, don't worry, we'll talk about layer 4 in the next video. I just want you to be aware that it exists. We then take that layer 4 envelope and place it inside another envelope. This envelope has a destination address of the IP of the web server, and we'll call this envelope layer 3. We'll then put the layer 3 envelope into another envelope, and this envelope will have the MAC address as the destination. And we'll call this envelope layer 2. Now, keep in mind, the layer 2 envelope now has all the other envelopes nested inside, including our original letter requesting the index.html file. Okay, going back to our Ethernet frame, the frame on the top would be equivalent to our layer 2 envelope, and the payload section is where our layer 3 envelope would be nested inside. In our single network, everything was pretty simple. We look up a MAC address for an IP, and we make a request. But what happens if our workstation is on a different network than our web server? You can see in this example, our workstation is on the .2 network, and our web server is on the .1 network. Now we have an interesting problem. In order to make a request, we first have to look up the MAC address of our web server, but now that web server lives on a different network. The router, being a layer 3 device, will block any broadcast traffic, and this is important to prevent those broadcast storms, but now we have to figure out how to reach the other side. And just to make it clear, on the left-hand side of the router, only ARP requests from the 192.168.2.0 network can be sent. And on the right-hand side, only ARP requests from the .1 network are allowed. So how can we reach the web server if we can't even figure out its MAC address? To find out, let's take a closer look at the router. Each interface on the router has an IP address like I mentioned earlier. The convention is to use the .1 address for the router. The router interface on the right-hand side will also use a .1 address, but this time it'll be 192.168.1.0. Each interface will also have a MAC address associated with it at layer 2. The job of a router is to route traffic to different networks at layer 3 using different interfaces. To handle this, the routers have a mapping for each network and the interface it will use to reach that network. This mapping is called a routing table. So for example, if you have a request that's destined for the 192.168.1.0 network that's on the right-hand side, we'll send the request out the Ethernet port also on the right-hand side, which is called Ethernet 1. Next, we'll set up our workstation so we can communicate with the web server. To do this, we'll need 3 pieces of information. Number 1, we'll need an IP address for our workstation. Number 2, we'll need a subnet mask to define the network and the sizing. And finally, we'll need to define the gateway that will point to the IP address of our router. Now that our IP address is set up on our workstation, we're ready to send our request to the web server, which lives on the other network. Okay, I know this is probably getting a little complicated, so let's use our letter analogy again to help us out. So here we have our HTTP request, and we'll place it into a layer 3 envelope. The destination is the IP address of the web server, which lives on the other network. We then put our layer 3 envelope into the layer 2 envelope, but we need a MAC address to send out our request. Again, because our router is blocking any ARP requests from other networks, we can't use the MAC address of the web server. So instead, we'll use the MAC address of the router's interface. Now we can send a request to the router, and here's the envelope that contains all the other nested envelopes. The router will open up the layer 2 envelope so it can inspect the IP address. This is done by the router opening up the payload section of the Ethernet frame. The router will then use its routing table to figure out which interface it should send out the request. In this case, it'll send it out the 192.168.1.1 interface on the right-hand side. The router then gets rid of the original layer 2 envelope and performs an ARP request against the 192.168.1 network to get the MAC address of the web server. It'll use the MAC address as the new destination. It then takes the original layer 3 envelope with the IP address of our web server and puts it into the new layer 2 envelope. This request is then sent down the right-hand side of the router onto the web server. Now, one thing to keep in mind is this process would repeat itself if there were more than one router in the way, where the layer 3 envelope is placed into new layer 2 envelopes as it traverses the network. Okay, I think this is a good place to stop for today. In the next video, we'll move up the OSI model to layer 4, the transport layer. Thanks for stopping by, and I'll see you in the next video.